All right, hello everyone. My name is Andrew Price, and let's dive right into it. Okay, so for this first lecture, we're going to need a large pot, and then we'll start boiling some water. The second step. Oh, no, I'm sorry, that's the wrong presentation. Wrong course. Yeah, this is better. Okay, right. So the space debris problem. So in the context of AI for space, there's a lot of impetus, there's a lot of push for different applications and research of AI for space because of the space debris problem. There are a large number of applications for AI in space, but the space debris problem is largely what drives my research and a lot of research around the world. So first we'll talk about what the problem is. Then we'll talk about a potential solution for the problem. And then we'll get into pose estimation and how AI fits into that. And of course, then we'll talk about motion prediction, which is the next step after pose estimation and what we're trying to shoot for. So let's start with the problem.
Currently, over 128 million objects larger than a millimeter are orbiting the Earth, transforming the space around it into a junkyard. These objects range from inactive satellites to flakes of paint. But even a millimeter of cosmic junk traveling at extremely high speeds can be catastrophic to many satellites that connect us around the world.
So as indicated in the video, there is a lot of debris in orbit. And the amount of debris is unfortunately only increasing. So here we have some simulations showing the amount of debris. And up in the legend there, we see PMW, which stands for post-mission disposal, which means after the mission is complete, do we deorbit the satellite? And if we continue to not have strong post-mission disposal guidelines, we can see that the amount of debris and fragments will continue to exponentially increase. So if we have debris in orbit, is that a big deal? Yes, it is. As it also mentioned in the video, a collision in space can be quite catastrophic. Of course, orbital speeds can be, thousands of kilometers per second. And with this amount of energy that's released upon a collision, it's just absolutely devastating to whatever objects are involved. Additionally, satellites are not particularly robust objects, so a collision would essentially destroy any type of satellite or human vehicle up in space. Okay, so it's a big problem. What's a potential solution? Of course, active debris removal is the most obvious solution. So there are a number of projects in place around the world, and one or two that have also finished. In the top right, we have some nice imagery from the ESA Clear Space project. This project is still ongoing. Actually, the planned launch time is 2025. And in the bottom right, we have a JAXA Kiku 7 demonstration. And this is something that actually happened. So here's another short video clip.
In 2018, a satellite called Remove Debris was able to successfully deploy a net around a dummy satellite, simulating a technology that might one day capture spaceborne garbage. In another technique, the satellite used its onboard harpoon to puncture a target panel that's about 5 feet away. The European Space Agency awarded a contract to ClearSpace, a Swiss startup, to retrieve a 220-pound piece of rocket debris that had been orbiting Earth since 2013. Scheduled for 2025, this mission will utilize 4 robotic arms to capture the debris.
Okay, so we've talked a little bit about the potential solution for removing orbital debris. But let's talk a little bit more specifically about how that might happen. So if we're going to remove some debris from orbit, the first thing we have to do is, of course, choose the debris, and then rendezvous with the debris, capture the debris, and dispose the debris. So that's kind of our 4 general steps. So when selecting the target, what kind of things do we need to consider? Well, what orbits do we care about? Where are we launching more satellites? What orbits are already the most crowded? This is important. Additionally, what targets are the most important to remove? Some targets are more dangerous or more volatile than other targets. Maybe they're too large, or maybe they're breaking apart in space. And then those would be optimal targets to remove to ensure the longevity of a healthy orbit. And additionally, are the properties of the target known? How long has it been up there? Is it breaking apart? Do we have information from when it was launched? These are all important questions. The next step, of course, is to rendezvous with the selected target. And in that case, is the target easily tracked? So do we have a good bead on where it is? Are we tracking it with various observatories or modeling its its orbit? Can the target be captured? So some targets are maybe too large, some targets may be too heavy, some targets may have components sticking out that make a net unable to fully unwrap it. So there's definitely some considerations there. Can the kinematics be estimated? So that's where we're going to start. That's the bulk of what I will be talking about. But essentially, can we estimate the motion of the target? And then finally, once we've selected the target, we've rendezvoused with the target, how are we capturing the target? So as we saw in the video, there's a net, a robotic arm, and projectile are all options. But we also have to ensure that the capturing robot, the service robot, will not be damaged by whatever by whatever application we choose. For example, if we have a fast spinning target and we try to shoot a harpoon at it, will the harpoon get caught and then jerk our chaser satellite in an unpredictable way? If they collided, we could lose both satellites. This is a very expensive endeavor. And finally, disposal. So how are we going to dispose of the object? We can increase the drag of the object so that the very low atmosphere at low Earth orbit can eventually pull the object down. We could manually adjust the target's orbit by bringing it down to Earth. Of course, that's an expensive option in terms of fuel. And there's other exciting things like an electrodynamic tether, which works with the Earth's magnetic field to generate a force. So we have limited experience with some of these tasks. We do have a lot of experience with other tasks, but what sort of things should we be focusing on from a research perspective? Well, for example, we can look at what JAXA is researching or what they're focusing on. One of those is space debris observation. Another one is, of course, space debris environmental modeling. So they're, of course, curious, how are the orbits projected to be over time? Another one, of course, is the experiments with space debris rendezvous. They've also done space debris capture simulations. And finally, they have looked at proposals for different debris removal systems. So just from looking at JAXA specifically as an example, we can see that they're looking at a broad variety of different research avenues, which are all coming to the same problem of orbital debris removal. So today, I'm going to be talking primarily about the pose estimation, which is part of the rendezvous stage, I guess.